So now we've defined the latent variable for a Markov chain, which is a sequence of states, S1 through ST. So we have a state S is a value between 1 to capital S, which is an index of the finite number of potential states that we can be in at any given time. And then a sequence of these states, S1 through ST, so a sequence of length t of states where each entry in this t-dimensional vector is a number between 1 and capital S, is called a first-order Markov chain if the joint distribution of that sequence can be written as follows. So we have a joint distribution of a sequence of length t. We first write that using the chain rule of probability. So this is always true in every case. We can say that the probability, the joint distribution is equal to this product of conditional distributions, where we have first the distribution on the first state, and then a product over the subsequent states of the probability of the state at time u, given all of the states up until time u. So this is always true. We can always condition on more than necessary and say that this is a way of representing this joint distribution. But now the first order Markov chain makes the additional assumption that this conditional probability distribution can be written this way. So the probability of where I'm at any time point u is not conditioned on everything beforehand, but only on the previous time point. So the distribution of where I'm at time u simplifies to being only conditioned on the distribution of where I'm at on the location, the state that I'm in the previous time point. So notice that this is a very simple modification of the IID assumption. For the IID assumption, we said that the joint distribution of t random variables is equal to the product of the distribution of each one individually. So this joint distribution, when we make an IID assumption, simplifies to a product of the distribution of each one separately or independently of any other point. Now the Markov, the first order Markov assumption, simply says that the distribution on a given time point is conditionally dependent on the value of the sequence at the previous time point. So this is the simplifying, this is the assumption, the distribution assumption made by a Markov chain on a sequence of random variables. It's a very simple modification, but the algorithms that will accompany it and the applications that we can put it to will be fundamentally different. So we're going to have fundamentally different modeling capabilities with this type of a model assumption compared with this type of a model assumption. So now to see how these conditional probabilities map to the Markov transition matrix, we can simply write it this way, that the probability of transitioning from state I at time t minus 1 to state j at time t is equal to the ijth element in this transition matrix. So this matrix, if there are capital S total possible states that the Markov chain can be in, then this is an S by S matrix where we're going to assume that every single row is a probability distribution. So every row has non-negative values along that row, and they each sum to 1. And the jth column in the ith row is the probability of making a transition to state j, given that I'm in state I. And so we make this assumption that the probability distribution on transitioning between every single state is not dependent on time. So this is another modeling assumption that we're going to make for the first order Markov chain, that the probability of transitioning from state I to state j is the same for all time points t. And so now, given a starting state, S naught, we can actually generate a sequence, a first order Markov chain on S states using this S by S matrix as follows, where given our starting state, we continue to generate new states where at time t minus 1, we generate the state at time t using a discrete distribution where we pick out the row of the transition matrix M indexed by the state that we're in at time t minus 1. So given what state we're in at t minus 1, that indexes the probability distribution that we're going to pick from M to then transition to the state at time t. And so this ST will be equal to K with probability equal to the kth entry in this row that is picked out by the state at t minus 1. So that's the basic model of a first-order Markov chain. It's very simple, very straightforward. But now we have a few problems. First, of course, as usual, we make the modeling assumption where we assume we know the model parameters, and then we get the data, the sequence in this case of state transitions. But then in reality, what we have first is the data, the sequence of states, and now we want to go back and infer the latent variables or the model parameters. So in this case, that's the Markov transition matrix. So let's look at a simple maximum likelihood. It's very intuitive. What we want to do is we want to find the transition matrix M that maximizes the probability of an observed sequence. And we know that we can represent this by taking the log of this likelihood and maximizing over M. And given the Markov assumption, what that amounts to is maximizing over a sum of every single transition's likelihood. So here we're summing over every single transition. We have a sum over the index, the states at two different time points. So given we're at time u and we're in state I, and we make a transition from state I to state j, where we're now in at time u plus 1, we have to now sum over all of those possible indicators to pick out the correct event, and then that is going to pick out the correct log probability. So this is the log joint likelihood of an individual sequence given M. And now if we just take the derivative and maximize subject to the constraints that M only has non-negative values and that each row has to sum to 1, we can find that the maximum likelihood transition matrix for transitioning from state I to state j is equal to the sum of the total number of times in our data set or in our sequence that we make this transition. So we are summing here an indicator of transitioning from state I at time u to state j at time u plus 1. We're summing over every single time point. And so this numerator is summing the total number of times we actually make the transition from state I to state j. And then the denominator is summing the total number of times that we are actually in state I to begin with, which would then give us the total number of times we transition from state I to any other state. So this is counting the number of events of going from I to j, and then this is normalizing so that when we sum this term over j, we sum to 1. So it makes a lot of sense. It's very intuitive, the maximum likelihood solution for the Markov transition matrix. For example, if we wanted to model the probability that it rains tomorrow, given that it rained today, all we would do is get a sequence of events where every single time point would be a day, and we would have an indicator of whether it rained or not in that day. And then we would sum the total number of times that it rained 2 days in a row, and then we would divide by the total number of times that it rained, period, and that would be the fraction of times that we saw rain 2 days in a row.